Evening, everyone. Welcome to the fourth Digital Twins webinar. This one is going to be focusing on integrating AI machine learning and geophysical models to forecasting and simulate air quality. And we have Dr. Manju Yu and Dr. Fengshu Zhang to co-chair this webinar. Dr. Manju Yu is a professor at Penn State University and directing the Geo Lab. And Dr. Zhang is a professor at our Scala School of Public Policy, and she has been focusing on the policy impact of climate change in the past few years since she's doing her PhD research. So Dr. Yu and Dr. Zhang, please take it away.
Cool. So today we focus on geophysical-based modeling and AI machine learning-based modeling for air quality. And we have diverse groups from different agency institutions. And we hope to have a deeper insights on how digital twins technology can be used in environmental modeling, advanced modeling especially. So today we will have two keynote speakers, Dr. Muhammad from California State University, Los Angeles, who will share the insights on how to use machine learning, AI to predict what we breathe. And then we will have another keynote speaker, Dr. Wenfu Tang from NCAR, who will present the recent development of Musica, which is replacing Wolfcam, a multi-scale model for air quality. So let's have our first speaker, Dr. Muhammad Pohamayan. Muhammad is an associate professor of computer science at California State University, Los Angeles. His research is focusing on using AI/ML for data for healthcare, air pollution, urban problems, climate change, and other social good applications. Muhammad, the floor is yours.
All right, thank you so much. Can you see my screen?
Yes.
All right. Good morning, everyone. Good afternoon for those of you who are on East Coast. Thank you so much for the introduction. As Manju mentioned, I am an associate professor of computer science. I'm also the director of artificial intelligence and data science research lab at California State University, Los Angeles. And today I want to talk about our project, artificial intelligence to predict what we breathe, and also creating a digital twin model for air quality. So this is a project originally funded by NASA 4 years ago, and it's in collaboration with the city of Los Angeles. So as we know, air pollution is the silent killer. We call it the silent killer because every year about 7 million people die from air pollution. It means that every 5 seconds, one person dies prematurely from the effects of air pollution. And many of them are children, unfortunately. And unfortunately, the minority and the low-income communities are the first victim. They faced higher exposure to air pollution and experience greater health impact. So this is our results, the results of our study in Los Angeles County. The left picture shows the asthma rate by neighborhood in Los Angeles County, and the right picture shows the poverty percentage by neighborhood in Los Angeles County. So as you see, there is a very big correlation between these two graphs. As you see, we have higher rates of asthma in the areas that we have higher percentage of poverty, unfortunately. So the first and the most important step in mitigating the air pollution risk is to understand the source of it, discover the patterns, and predict it in advance. But air pollution prediction is a very complex problem because there are many different factors are involved. So this curve, it shows the air pollution over 1 year, 2020 in Los Angeles. It's average air pollution in Los Angeles, PM 2.5 specifically. And as you see, this graph looks completely random, okay? But when something is random, it means that it's not predictable, it is unpredictable. But when we collect more data from other sources, it turns out that it's not completely random. So here in this picture, again, the blue curve shows the PM 2.5 values. But this gray curve above that, it shows the wind speed. So obviously, as we see, there is an inverse correlation between wind and air pollution. So every time the wind is higher, wind speed is higher, the air pollution is lower. And the green area is the average of air pollution in the past 2 years before that, in 2018 and 19. And as you see, again, we can see a big correlation between the historical data from past 2 years to the air pollution of 2020 to 2020. So it means that if we use historical data, and using machine learning algorithms or anything that can learn from historical data, we will be able to some degree predict air quality. Right here, you see a very big peak on PM 2.5 values, and this is 4th of July, okay? So the firework on 4th of July, as you see, it creates a huge peak in the value of PM 2.5 in Los Angeles. These orange areas, these orange bands, they show a big wildfire that we had back in end of summer in Los Angeles. And again, as you see, this wildfire created a very big peak in the value of both of them, created a peak in the value of PM 2.5. And right here, so I showed this the data of 2020 because we see an interesting pattern here. Right after pandemic declaration and this lockdown, as you see, there is a reduction in the value of PM 2.5 in the city of Los Angeles. We guess it was a part of that was at least because of the lockdown, and another part was because of the rainstorm that we had in 2020, in March 2020. So it turns out that it's not completely random. Same thing for NO2. When you check NO2 pattern, again, we see a big inverse correlation to the wind speed. The data is very much correlated to the same pattern that we have in previous years. Other factors like special events like 4th of July wildfire, etc., has significant impact to the level of air pollution. So if you want to accurately predict air pollution, we need to take into account all factors that have impact on air quality. We need to collect, process, and use those data from many different sources. We need to process that. And we need, if you want to use machine learning on AI technology, this is what we did, we need to develop a complex machine learning model, because the data is very complex. It comes from many different channels. So we need to design and develop and train a very complex machine learning model to be able to discover, extract, and learn those patterns from the data. This is what we did in the past 4-5 years. We have been working on this research. So these are some of our results for predicting PM 2.5 in Los Angeles. So the orange curve shows our prediction. The blue curve shows the ground truth. As you see, we can now predict air quality with very high accuracy. These predictions are based on the satellite data, ground-based data, meteorological data, wildfire data, and etc. So this graph right here, it shows our prediction. Air quality prediction for Los Angeles County, specifically PM 2.5, but we have developed 12 different models for predicting 6 major air pollutants in long-term and short-term, both short-term and long-term. By short term, I mean hourly predictions in the next 48 hours, and long-term prediction is daily prediction up to 10 days in future. The accuracy of our prediction was about 95% in predicting PM 2.5. And as you see here, the temporal and spatial resolution of our predictive model is very high. We can predict on hourly basis with a spatial resolution of 250 square meter. So each one of those small tiles here is like 250 square meter that we can, it's like neighborhood scale. So we can predict for each neighborhood with high accuracy. So we use, as I said, several big data set, very big data set for this purpose. The data includes satellite images from NASA satellites, from ESA satellites, and the data includes wildfire information, as well as ground level sensors from both reference sensors, reference high quality sensors, reference-based sensors from EPA, as well as low cost sensors. Many of those sensors are like Purple Air, they are community maintained sensors, as well as meteorological data such as wind speed, wind direction, temperature, humidity, etc. And each one of those data sets needs its own data pre-processing and cleaning, outlier removal, missing value imputation, feature extraction, etc. These data sets are from different scales. Some of them have, for example, high temporal resolution, like ground-based sensor data. We collect data on every 5 minutes or every minute. But some of those data, like satellite data, they have we collect them on daily basis. On the other hand, sensor data has low spatial resolution, but satellite data usually have higher spatial resolution. And we developed, as I mentioned, 12 predictive models. They are all based on very deep neural networks models that we have developed and trained. We needed to develop several models for processing different parts of the data. For example, meteorological data, it needed its own neural network model, deep learning model to pre-process that first, perform dimensional reductions, etc., and then use it in our predictive models. Let's take a look at some of our results. So we validated our data, our predictions, only based on high quality reference sensors by EPA. We have 7 of them in Los Angeles County, and these are our 48-hour prediction accuracy for specifically PM 2.5 based on the ground truth value collected from those sensors. Also, this is our daily prediction. 2 days in future, 4 days in future, 6 days in future, etc. And of course, this is normal as we move forward to the future, like 10 days in future, the accuracy of prediction for 10 days in future is lower than our prediction for 2 days in future. Same thing for other air pollutants. This is ozone. We have, I believe, 13 sensors, reference sensors in Los Angeles that we use to validate and our data to evaluate the accuracy of our predictions. And same thing for NO2 and other air pollutants, as I mentioned. One interesting, this graph shows an interesting results that we achieved by using wildfire data as another input for our predictive model. We could improve the accuracy of prediction. Of course, wildfire is a huge problem in California, and it is actually one of the main sources of air pollution in this state and also in Los Angeles County. By using that, of course, we received that data from different sources, including satellite images. We can improve the accuracy of our predictions. We also applied this model on some other cities. We wanted to try it in different continents. One of those cities was Mexico City. Mexico City, the city of Mexico City, they has a very good sensor network for measuring air quality on ground level. So we use those values as ground truth for evaluating our predictive models, and these are the accuracies in different locations of the city. Another city was London in England. Again, we tried our predictive models in collaboration with all of those things. So this case study was in collaboration with the city of Mexico City. They provided data to us. And again, this one was in collaboration with the city of London in UK. And they provided us the ground level sensors, and we could validate our models. And the other one is Durban in South Africa. This city has only 4 sensors, but the city of Durban was really helpful. They provided the data to us and helped us to evaluate and validate our predictive models. Another part of our project was to develop a digital twin model for air quality, and specifically the connection between air quality and transportation. So when we talk about digital twin, the digital twin technically is a digital replica of the real world. It's like a virtual representation of our physical world. And the difference between digital twin and other traditional simulations that we have been using for many, many years is that digital twin usually receive real-time data as well from IoT or from other sources. And it takes into account in this real-time data into visualization and calculations. Also, a digital twin can be equipped with it can include AI models, data analytics systems, machine learning algorithm, etc., to get better insights from data. Specifically, one of the applications that we were very much interested was to use digital twin to understand air quality data, to visualize it, get insight from that, and more importantly, for the city of Los Angeles to understand the connection between air quality and transportation. So this digital twin model used to visualize AI-based air quality predictions that we performed, as well as understanding and visualizing the connections between transportation and air quality in real time. So the city will use this model to visualize and model what-if scenarios showing the impact of changing the modes of transportation, adding a new subway line, for example, a new metro line, adding some new streets, some highways, changing the topology of the city design, and understand the impact of that on air pollution in advance and air quality in advance. This is one of the important goals of developing this digital twin. So in this part of the project, we developed a real-time system that can map transportation into air quality, and it was not an easy problem, because when we talk about transportation, what we need here is traffic count, and traffic count is not necessarily available in many areas. Okay, so in some main intersections, for example, in the city of Los Angeles, there are some systems that can count traffic, some sensors, magnet loop sensors that count cars, or some type of cameras, but they are very limited. We only have them in very specific, only in some main intersections and highways. The way that we developed system was to mapping a traffic flow to traffic count, and it was a complex problem. So we used statistical modeling for every street based on the traffic history of that street, based on the number of lanes of that street, and the type of the street, the connection between the street and intersections, to convert traffic flow into traffic count, and then use a statistical models to estimate the amount of air pollutants created by those cars. So I'm going to show you this example. So this graph shows the real-time value of PM 2.5 created by vehicles per second in Los Angeles County. And as you see, we see higher value of PM 2.5 in rush hours, for example. And this is NO2. So again, we can see the NO2 values in real time. You can see the value of NO2 increase in rush hours. And these are the information that are very important for the city of Los Angeles, or every city, to redesign the city structure and in our digital twin model to see the impact of changing the mode of transportation on air quality. And again, this is CO2, which is one of the main greenhouse gases. NO2 and CO2 both are two main greenhouse gases that are important for the city of LA to deal with climate change, to address the climate change issues that we have. So in summary, if I want to summarize this talk, we have developed, first of all, we integrated big data from various sources, including satellite data, ground level data, and etc., meteorological data, wildfire data. And each one of them we receive from many different sources, for example, NASA satellite as well as ESA. As I said, this part was very challenging because data is in different time scales and they have different resolution. So again, sensor data, for example, ground level sensor data usually have very low spatial resolution because the number of sensors are limited, but it has very high temporal resolution because we can collect data on every minute or every 5 minutes, something like that. On the other hand, satellite data, it has very high, usually spatial resolution, but it has very low temporal resolution because we can collect data from some of those satellites every 48 hours or every day. So a big part of the work was to align this data. We needed to do sampling, we needed to do interpolation to make sure that the data are in the same scale to be able to use it in our system. And then we developed, again, advanced AI machine learning model. All of our algorithm based on deep learning, but different types of algorithm and deep learning model to process different types of data. And the goal was to predict air quality with very high spatial and temporal resolution. We created digital twin model to extract insight, to do visualization, data integration, and in this specific application to understand the impact of the transportation, the connection between air quality and transportation, and also health. So the city of Los Angeles wants to know what will be the impact of changing the mode of transportation or adding new modes of transportation to air quality and to the citizens' health in advance. And another goal, of course, is for the city is to improve environmental justice. As I said, our study shows that unfortunately, the minority and low-income families, they are exposed to higher levels of air pollution. And one of the goals of the city of Los Angeles is to address environmental justice. And I think that is for my talk. Thank you so much for your time, and let me know if you have any questions.
Thank you, Mohammed, for the wonderful presentation. It's also interesting to see the digital twins example after the Los Angeles example. And you have probably expanded through multiple cities. That's also interesting to see.
Right.
We have around 5 minutes for the audience to ask our first keynote speaker questions. If you have questions, you can put them in chat or open your voice. To start the process, yeah, we have a question. I guess since this is a webinar, all of us actually can see the question in chat. Mohammed, would you like to take your time, read it?
Yeah, I'm reading this now. Well, among the data set that we use, which one was more important? So of course, this the ground level sensor data is very important. This is one of the most important data sets that we use in our model. But again, one issue that we have with ground level sensors is that the spatial resolution of that is very low. So as I said, okay, so we have two different type of sensors. We have high quality reference sensors, and we have low cost sensors usually maintained by usually their community maintained sensors. So for low cost sensor, they only measure PM 2.5 or PM5 and PM10. They don't measure, I mean, those low cost sensors that they have many of them. They don't measure other type of air pollutants like NO2 or ozone or other things. That's why in many cases we only have especially for other air pollutants other than PM 2.5, we need to use those reference sensors that the number of them are very limited. They are very well maintained, and the EPA calibrates them on timely basis, but the values are accurate, but the number of them are very limited. So in Los Angeles, we have only like about less than 10 reference sensors that measure PM 2.5. That is why we rely on other data sets like satellite data that has high spatial resolution. But again, those ground level sensors are very important here. The number of them are very limited. Another thing about ground level sensors is that they are important because we use them to evaluate our model. But in our case, in our project, we only use reference-based high quality sensors to evaluate our models. That's why we need them. And your second question. Yes, many of those data sets are public. Many of those data sets are public. The ground level sensors are usually public. Many of those satellite data is also open source, and some of those data sets maybe originally are not open source, but if you contact the sponsor or the company, the organization that provides the source of data for the sake of research, they make many of them open source for you. And okay, one of the data sets that is very challenging to find for open source, if you want it open source, is health data. So when we want to, this is what we are doing right now. Another part of our study is to understand the impact of air quality on health based on like high resolution data. So public health data is available. Some kind of health data is available as an open source data sets, but the granularity of the data is very low. Again, the spatial resolution is very low. So one of the data that's very challenging to find high quality data for this application is health data. And we are now working with several health organization companies to work with their data on our project.
Thank you. I have a follow-up question on your other cities projects. We know that in the United States, data sets are usually publicly available, like
Right.
other than health data, like emission data, traffic data. How about your case studies in, for example, South Africa? What are the city governments providing? Are they providing the emission inventory?
Yeah, very, very good question. So as you said, the sensor data is public. Many of them are public organizations, and the data is open source. This is open data. But for other cities that we have worked so far, the data was not public. No. So we contacted the city of London, for example, or the city of Mexico City or Durban. And we had several meetings with them, explained our project, showed them several study cases, and then case studies, and then they kindly shared their data with us, especially the sensor data. And those sensor data, they are maintained by the city of London, for example, or the city of Durban, and only the city had access to that data. So after several back and forth, a lot of meetings and conversation, they shared data with us and helped us to evaluate our predictions based on that data.
Thank you very much.
Some of those data sets are public for some cities. I know that, for example, through OpenAQ, you can get access to some public data from some cities. But again, some of those reference data is not public, and you need to contact the city specifically and to get access to the data.
Thank you very much. Dr. Wenfu Tang, who will introduce us to NCAR's recent development of Musica, as I said. Dr. Tang is a project scientist at NCAR's Atmospheric Chemistry Observations and Modeling Lab. Her research focuses on fires, fire emission, and their impact on atmospheric composition and chemistry using models, satellite retrievals, field measurements, and data assimilation. Dr. Tang, please take the stage.
Can you hear me okay now?
Yes.
Okay, great. Hello everyone. I'm Wenfu Tang from Atmospheric Chemistry Observations and Modeling ACOM Laboratory at the National Center for Atmospheric Research. I would like to thank Manju for inviting me to give this presentation. Today, I'd like to talk about air quality modeling and Musica, a community model for atmospheric chemistry and aerosols. Here's the outline for this presentation. Because the audiences have various background, we will start with a general introduction to air quality modeling. Before I talk about air quality modeling, I want to point out that modeling is part of a large framework to further our understanding on air quality. Besides modeling, there's observations from field campaigns and remote sensing that can be used to improve and validate models. And there's data assimilation to understand the uncertainties and provide ensemble forecast. And there's computing, which is important because it enables new technologies. And there are process models and fundamental knowledge that are used to inform model processes. And most importantly, air quality models are usually developed with and for the larger community. for purposes such as research and operation. So why do we need models? Here are a few example applications. Models can be used to predict past, current, and future air quality and atmospheric composition. It can be used to explore the interactions between weather and atmospheric chemistry, studying the role of chemistry in climate and their feedback, and also understanding the biogeochemical processes that govern the composition of changes to the natural environment. And also models can be used to support the interpretation of observations and assessing the value of current and future observational systems. And the list can go on. So in general, we need models to increase our understanding of atmospheric chemistry and to develop tools to provide societally relevant information. So what is an air quality model? Here I'm showing a basic schematic of processes that go into an air quality model. Here the model is simplified. A model is a simplified representation of the complex system. And here on the left, in this box, I'm showing the major processes that are relevant to air quality. So there's emissions of air pollutant and their precursors and the deposition, and there's chemistry processes in the atmosphere. And of course, there's inflow and outflow that change the transport of the air quality. And on the right, I'm showing this. As you can see, this Earth, or in general, a domain of model is divided into these many little boxes, and each box will have all these processes shown on this. It is important to keep in mind that a model is only as good as the understanding we put into it. For example, if there's any process we don't know that's missing in our understanding, it will be missed in the model. And models are not the truth, but if we correctly identify their strengths and weaknesses, they will be extremely valuable. Our models not only need to represent a number of complex processes, but also a wide range of scales from local to global scales. Depending on the problems you are trying to address, air quality modeling generally can go from global scale to local scale. However, these scales are often decoupled when we study them. As an example, the urban scale all the way down to the building level are important to exposure, but research focusing on this scale are often decoupled to the larger transport. We also see this separation of scales in the modeling system we are using. Currently, there are separate models to deal with research at local, regional, and global scale studies. For example, when we look at a very small scale, people in general use LES model and CFD models, and there's regional models to look at regional air quality, and there's global models when people look at global transport. So now the question is, can we simply divide research topics by scales? Probably not. Air quality is a cross-scale problem. To fully address air quality, we will need a unified model to seamlessly cover the local emission scale all the way up to the global forcing scale within a single framework. In addition to the scales, the atmosphere is connected to other components of the Earth system, such as the land, ocean, and humans. So we need a system that includes these connections so that we can use them to fully address these issues. So do we have such a unified scale-aware framework? Yes, we do. So now let's talk about Musica. Musica is the multi-scale infrastructure for chemistry and aerosols. It is a new model-independent infrastructure which will enable chemistry and aerosols to be simulated at different resolutions in a coherent fashion. So on the right here, I'm showing our goal for the structure of Musica. First of all, the vision of Musica is to have a modular framework that facilitates the use of a variety of chemistry schemes, physics parameterizations, and atmospheric models. It is also coupled to other components of the Earth system, such as land ice, land, ocean, CS, etc. Therefore, it allows us to study the connections between climate and air quality. And also it has a whole atmosphere, so it can be used to study the stratosphere and above and their interactions with the troposphere. A key component of Musica is MICM, the model-independent chemistry module. MICM maintains the chemistry schemes through a database. Thus, it allow easy and traceable updates and automatic generation of computer code. MICM is designed to enable linking to any 3D or 0D model. A 3D model is the model the Musica model we just talked about. And 0D model is in general a box model. So this MICM can also be used by non-NCAR models, and we make it efficiency and flexible for other next generation models. We have also developed a MICM-based box model. It's called a music box. It has a browser-based and a terminal-based version. And here is an example of how it looks like in a browser-based version. Music box is easy to use, and it has been used for exercises, for classroom instruction and tutorials by a few universities listed here. And if you are interested in using it, please check this website or contact us. So we have talked about the concept of Musica. Here, I'd like to present to you the Musica version 0, which is already available as a configuration of the Community Earth System Model, CESM. And on the left, I'm showing a standard grid for the Musica version 0 with regional refinement over the continental US. As we said, Musica version 0 is released in CESM. So let's briefly look at CESM. CESM is a fully coupled global Earth system model. It has atmospheric chemistry, land, ocean, CS, land ice, rivers, etc. These components. And these Earth components are coupled together using a coupler. So CESM provides a state-of-the-art computer simulations of Earth's past, present, and also future states. Musica version 0 is a configuration of CAM here, and it is always coupled with land and have the option of coupling with other components. And here are a few examples of current applications of MUSICA version 0. There's the default grid for continental US, and there's Arctic grid, Asia grid, Africa grid, and Australia grid. And here is an example of very high resolution grid over Korea, or a relatively small area, but still with a global coverage. And if you want to know more about all the available grids, please check this website. Here is another example of MUSICA version 0 grid. So it has 3 refined regions to replicate the 3 upcoming geostationary satellite constellation for atmospheric composition, as shown here on the right. So this grid is currently being tested. And this is one of my favorite examples of MUSICA version 0. So it has multiple regional refinement over selected urban areas globally to address urban air quality at high resolution, meanwhile still consider the global and large-scale transport and impact. And I want to point out that the examples we have seen are all based on MUSICA version 0, which used a spectral element dynamic core as demonstrated here. So it looks like this. We are also developing MUSICA version 1. It is currently being tested. So MUSICA version 1 will use this MPass dynamic core, and this is what it looks like. MUSICA version 1 will have higher resolution, and it can go even to higher resolution, higher than 1 kilometer in a selected region, meanwhile still cover the whole globe. So since MUSICA version 1 is still being tested, the examples I show here will all be MUSICA version 0. Here is an example of modeled large-scale transport of fire smoke here from Western US using MUSICA. Let's see. The smoke took a trip to Canada and then come back to impact air quality in the East Africa. Oh, sorry, East US. This is for 2020 summer. Yeah, so it captures the large-scale transport. And here, let's look at this figure on the right. On the right, I'm showing an example of a small-scale fire plume modeled by MUSICA version 0. So the black line is aircraft track that sampled the fire plume during a fire execute field campaign. And the colored grid are MUSICA grids, and carbon monoxide concentrations at the surface are shown here. So as we can see, the resolution of MUSICA version 0, it is approximately comparable to the fire plume and the 1-minute merge airborne observations. Here we can see that MUSICA version 0 can simulate high resolution fire plume, and meanwhile the large scale global transport of fire smoke at the same time. And here is another example. So I developed an Africa configuration in the new MUSICA version 0 model as shown here on the left. So I conducted a model simulation for the year 2017. And then I compared the model results with a few satellite retrieval products over this continent. And on the right, I'm showing the model satellite discrepancies. Using these model satellite discrepancies, we were able to identify a region to conduct a potential field campaign in the future. So if we conduct a field campaign in this highlighted area in the future, we will be able to significantly understand the model satellite discrepancies and improve our model predictability. And here is another example of Musica supporting the Eclipse aircraft field campaign. Eclipse took place over Asia in 2022 to understand Asia summer monsoon. And the Musica grid used is shown here. And using this configuration, Musica simulates the convective transport of pollutants by the Asia monsoon into the upper troposphere and the lower stratosphere. Great. And here is an example using Musica to study Korea air quality and understand the impact of model resolution. So the grid used in this study is shown on the here. So long story short, model resolution has significant impact on simulation of ozone and its precursors in urban regions. So for more information, please check this paper, GEMS, published in 2023. So Musica has also been used to study air quality in South America. The goal of this study is to understand the impact of biomass burning on air quality across scales. And here I'm showing the modeled ozone and PM 2.5 in this region. I've only showed a few examples due to the limited time. If you would like to know more about our current studies and applications, please contact me. Hereafter, I would like to talk about a few other model relevant activities we have been doing at our lab that I think that might be of interest to this group. So at NCAR, we provide forecasts. We have a near real-time file emission product called FIN, file inventory from NCAR. FIN provides near real-time file emission estimates for the whole globe. And FIN is then used as input for the WICOM chemical forecast for the whole globe. WICOM is a whole atmosphere community climate model. We provide a global air quality forecast at 1 degree by latitude by 1 degree longitude resolution. And then we also provide a WolfCam forecast for air quality in continental US. WolfCam is a regional model with relatively higher resolution. It uses the WICOM forecast as boundary conditions and also use FIN as input for fire emissions. And this is also, I think the resolution is 12 kilometers. And we also do chemical data assimilation. So my colleague Ben Gobert is the one at our lab mainly working on this. The data assimilation tool we use is called Data Assimilation Research Test Bed, DOT. DOT is a community and open source software. It uses sequential and ensemble DA technique. And we use DOT to assimilate satellite observations into CESM. And we are currently developing the capability of using DOT together with Musica. So coming back to Musica, we have conducted a few tutorials for using Musica and using Musica output. The past tutorial has been recorded, and please check this link if you want to see the record. You can also join our mailing list through this link here, or simply send me an email. I will sign you up. We are likely to have tutorials again in the future. And we have conducted a community Musica version 0 simulation for the year 2012 and 2013. It's called a community simulation because the results will be open to anyone who wants to look at it. So if you want to use it, please make a request, or you can send me an email. I'll connect you to right people. All right. Here I would like to end my presentation with the goals of Musica. Musica is to be developed collaboratively with university and government researchers. Musica is to become the next generation community infrastructure for atmospheric chemistry and aerosol research, and that includes air quality relevant research. And Musica is to contribute to both advancing the science and to provide relevant and actionable information for the development of mitigation policies or warning systems. Musica is an open access community model for anyone to use. So definitely check it out if you are interested. And with that, I'll stop here. Thank you.
Thanks, Dr. Tang, for this very comprehensive introduction of Musica and relevant work at NCAR. So we have around 5 minutes for the audience to ask questions. You can put them in chat or open your mic. To start off the process, I actually have a couple of questions, but I'll probably ask one. So as you showed in your slides, many cases like case studies, examples of Musica, they showed that scale changes in the model can significantly change the model's capability, like the predicting capability. But on the other hand, the goal of Musica is to provide flexible, higher resolution over targeted area while keeping the capability of the global simulation possible to have the out-of-the-box effects towards the targeted area. So these two goals are somehow contrasting or conflicting with each other. How do you see this conflict, and what is your goal to mitigate the effects from both ends?
Yeah. So let's see. So for the application, for example, if you look at this map, it really depends on your research interest. For this study, you cannot, like for example, you cannot study Africa biomass burning impact using this map. This map is designed to study the air quality over these selected areas. And outside that, outside of this these regions of interest, the model is still valid. It's just it's with coarser resolution, but it will still be capable to provide the long range transport and boundary conditions for your region of interest.
So defining,
yes.
So defining your target area is very important, and outside your target area is probably not inside the research scope. Is that what you're saying?
Yeah. Let's see. So comparing to a regional model, for example, for example, as shown here, a WolfCam simulation, you will need a global model to provide boundary conditions for you to do the simulation, right? For you to conduct a regional simulation. However, sometimes there's inconsistency with the boundary condition and what's going on in the boundary in the domain. Using a global model with regional refinement, you will be able to simulate everything in a consistent way. And there's also two-way interactions. What's happening inside will also influence the whole globe.
Yeah. Thank you. Any other question from the audience?
Can I ask a question? I'm a social scientist, so this is a great talk. It's eye-opening for me. I'm interested at the end of the talk. You mentioned you have a tutorial. It seems like this tool is open to the public, and you have a tutorial to teach people how to use it. Do you have any data on who are the users of this tool? What do you primarily use the data for?
For now, this is mostly used for research. It's not in for atmospheric chemistry research. We have a few collaborators from universities doing health impact using Musica, but we would like to see more use for more various purposes of our model.
Does that mean so far it's been primarily used for scientific discovery, right? Not some of the social application, social impact that is still under exploration currently?
Yes, you are right. If we would welcome any use of this model. If you are interested, please contact me. Please contact us. Yeah.
All right, thank you. I'll now hand it over to my colleague Feng Xiu to lead the panel discussion.
Thank you, Manju. Thank you, Dr. Tan, and thank you, Dr. Muhammad, for your great talk. So now we're transitioning to our panel discussion. Today we have the pleasure to bring together Dr. Thomas Huang and Nasu Marvelisi to discuss the opportunities and the challenges for integrated modeling of digital twins and air quality, using air quality as example. So Dr. Thomas Huang is from NASA, Net Propulsion Laboratory, and Nasu Marvelisi is from George Mason University. So, and Dr. Huang is going to talk about his perspective on practice and challenges on air quality, and Nasu Marvelisi will talk about how to integrate air quality data using AI and geographic models. So, Dr. Huang, if you are here, could you please share your thoughts on the current practice and the challenges in air quality?
Oh yeah, can you hear me?
Yeah. Yes.
All right. Hey, good to be here. Good to see some friends on this call as well. I was just in NCAR 2 weeks ago to give a seminar, so you might be able to find my talk at your YouTube channel. So I've been working on building digital twins. I think some of you already know. And the NASA's point of view, at least in the AIST program, the Advanced Information Systems Technology program, digital twin is more than just a numerical simulation. Numerical simulation definitely is a very important part of the digital twins. But they set the requirement a lot higher. The requirements really to be able to keep long-term records, so we know what's been happening in the past, and we can learn from the past, but also be able to understanding what's happening now. Like for example, the Canadian smoke, right? And also to be able to ask questions like, what if, right? This is very important for decision makers. So my projects actually collaborate with Mohammed in Cal Survey, but also with the deputy mayor of Los Angeles. And for Jean Home, well, she's fascinated about science, and she was a former JPL employee as well. But in her position, she's looking for actionable, right, recommendations, something that she can direct her team to do. But more importantly, because everything that she makes, right, it has to back up with solid science, right? So about the whole provenance and repeatability and reproducibility, right? So the bar is pretty high. So the whole point about digital twin is to try to integrate all these, latest observation. We're talking about satellites, model outputs, and in situ data, and also be able to use this latest observation to drive your next assimilation, your ML predictions. And based on those predictions, you can act on it, right? It could be a mitigation recommendation. This is the kind of thing that you could do. You could maybe tell people to wear a mask with certain sensitivity, or stay indoor, right? These are some of the things that are actionable that, to general public. But other actionable things could be, retasking an instrument, right? So my project is actually working with the NASA's upcoming mission, Maya, which is looking at PM 2.5 and connecting understanding the impact to health. Is supposed to be launching in 2025. And that instrument actually has a retestable camera. So imagine being able to run your analysis on ground with your model simulation and ML prediction, and use that to drive your next scientific observation, and be able to task all your digital or instruments and focusing on the sensitivity area. Like, for example, if there's a fire smoke start smoking over in Northern California, right? You want to take a digital observation and not just relying on one single instrument. Let's say you take it, maybe you can ask Topomi to take additional observation as well. So that's the whole part about agility. We call it the new observing strategy. That's the code word for it in the NASA AST program. But think about bringing all this data into one big environment. How do you make sense out of it, right? So you do also need a solution where you can have all this data, model observation, and in situ, that's compare them interactively, right? Be able to run these, look at them, and makes it easier for the user, right? You don't want to have the user download a bunch of files and do a bunch of regrading and all that. So our end goal is looking at focusing, delivering near production quality solution. And that means that taking all these interesting technology development here discussed today, how do you make it sustainable, right? We all talk about big data analysis, thinking about a knowledge graph and all of that. These are all interesting work, right? But how do you sustain it? How do you making sure that you can afford it? Do I need to hire an army of people just to keep this thing running, right? So that's the bigger question, right? We all can show some really interesting output, if we have infinite amount of resources. But how, like the end, the NASA, right? And I think, like many of you, working on nonprofit organizations, right? How do you make the solution sustainable? And it means that we have to be smarter about what data to bring in, right? We can just say, well, just bring all the data in one place. This is way too much data, right? NASA itself, we have lots of, we just, the SWAT mission is going to be generate 23 petabyte of data in 3 years. And that's a lot of data, right? That's just one instrument, one satellite. We think about in situ and all that, right? So the new challenge we have to look into is really how do we be smarter about data, what to bring in, and for how long, right? And part of the actionable work for as the digital twin might be relate to the dispatching value-added processing, right? You found something interesting, but you don't have all the information yet. So can I grab some additional measurement, but also put a new algorithm into the system, generate new product? And now we have another observation or another view of the same data. So being able to be on demand, be able to process value-added data is extremely important. So if you picture that, right, connect all this dot is how we connecting the physical world and digital world is it has to be a streamlined process that is in operate 24/7. It doesn't have, and for sure, it's not going to be one computer. It's going to be a collection of system, and it's going to be leveraging existing solution like the simulation, a model that's the presentation being discussed today that have experts already been running these things. Be able to pull in analysis by other center that actually have science experts, right? Data scientists that actually know how to work with the data. So think about is a federated multi-computing architecture that we're building so that now all boils down to be able to be getting all our data, digital assets, right? Data, model, output, prediction, all working together seamlessly. And that's the challenge, and that's the work that some of the folks on the call here working with me, Mohammed in particular, he had to stuck with me every week, right? Sorry. But also Phil, right? So, but it's one thing that we're doing is not just building an island, right? I'm a big open source advocate. I've been building open source software for more than 20 years. And I've been open sourcing software like this. Probably 30 JPL package with my name on it, right? Still growing. So the point is, we're building this digital twin as an open source framework. Part of that is me recognizing that we cannot solve the world's problem on our own, right? We need the community to come in, and you bring your data, you bring your model, and you know better how to integrate, how to make it work the right way. Right, so we make that as an open source framework, and then we using air quality for wildfire as one of the use case for digital twin. We also building another digital twin using the same framework for hydrology for flood. So the part is to use the best that we have available, right, in NASA to verify and validate our solution, and then make that available and encourage other people to contribute to this work. There's no digital twin standards. I think Ryan can tell you that. I see he's on the call here. But if you have an open source solution that actually brings in different standards and make them work together, right? That speaks volume than a stack of paper with printouts and hyperlinks, because now people can actually touch it and work with it. And so I'm really trying to push this as open source solution for as a reference implementation for digital twins for the community, right? Again, I acknowledge that we cannot build a digital twin just by NASA itself. We just don't have all the data. We don't have all the resources. We build a community. Imagine having a federation of digital twins that you can have them all work together from global to regional scale, right? Everybody else paid for their digital twin, but researcher can just connect these digital twin together and make some sense out of it. And that's my vision. So challenges, there's a lot of it, right? How to get all these things working together. And that's a big part. So standard is a big one. So this is why we are actively working with smart people like yourself. When you talk about what if questions, scenario-based questions, right? People want answer quickly, right? So most large model simulation takes hours, days, weeks, right? How do you get that fast? How do you make quickly, right? You might have to start looking at things like circuit models, right? You might have to have these model continues running 24/7, so incrementally improve these the output instead of having to rerun every single time, right? So looking for an opportunity to do that. Shortage of data. We don't have all the data. As much in each satellite we have, how many in situ sensor, we just don't have all the data. So I'm really excited about the recent Temple instrument, right? So I'm sure you all look at Temple, and I'm waiting for the data, right? They promise should be in sometime in spring or soon. And because that actually will give us an hourly measurement, what's happening in Northern America. That's exciting. Instead of waiting for 24 hours to figure out what's going on, now you get the next measurement in an hour. So we just don't have all the data yet. And Now we're fortunate we are in the populated, very industrial modern society here, but there's a lot of area that don't have the sensor data, right? You talk to Mohammed, I asked him, can you get your prediction model to run in this location? He said, we don't have data here, right? So it's a challenge, right? Not every part of the world have the wealth of data that we have. That's a real gap there. But I think at the end is really making things affordable over time, and like basically require people to be here, things outside the box, be smarter about what data to use, what analysis, and when to apply what method. And I think that's extremely important. So I encourage the group to think productions, all right, think operation. At the end, there's lots of great science research technology being done out there, and JPL been done a lot. And one thing I told the deputy director recently is that JPL did we create a lot of shelfware. They go, what shelfware? But because we created something for 2 years, 3 years, and we couldn't find infusion, it's just stuck in the shelf. and it's very sad, right? So my job is try to get all these exciting technology in the package, containable, manageable, and affordable solution that we can actually use, for the community. So that's it. I think it's my time up.
Thank you, Dr. Tan, and thank you, Dr. Mohammed, for your great talk. So now we're transitioning into our panel discussion. Today we have the pleasure to bring together Dr. Thomas Huang and Nasu Mavalizi to discuss the opportunities and the challenges for integrated modeling of digital twins and air quality, using air quality as example. So Dr. Thomas Huang is from NASA, Net Propulsion Laboratory, and Anasu Mavalizi is from George Mason University. So, and Dr. Huang is going to talk about his perspective on practice and challenges on air quality, and Anasu Mavalizi will talk about how to integrate air quality data using AI and geographic models. So, Dr. Huang, if you are here, could you please share your thoughts on the current practice and the challenges in air quality?
Oh yeah, can you hear me?
Yeah. Yes.
All right. Hey, good to be here. Good to see some friends on this call as well. I was just in NCAR 2 weeks ago, give a seminar, so you might be able to find my talk at your YouTube channel. So I've been working on building digital twins. I think some of you already know. And the NASA's point of view, at least in the AIST program, the Advanced Information Systems Technology program, digital twin is more than just this numerical simulation. Numerical simulation definitely is a very important part of the digital twins. But they set the requirement a lot higher. The requirements really to be able to keep long-term records, so we know what's been happening in the past, and we can learn from the past, but also be able to understanding what's happening now. Like for example, the Canadian smoke, right? And also to be able to ask questions like, what if, right? This is very important for decision makers. So my projects actually collaborate with Mohammed in Calsare, but also with the deputy mayor of Los Angeles. And for Jean Home, while she's fascinated about science, and she was a former JPL employee as well, but in her position, she's looking for actionable, right, recommendations, something that she can direct her team to do. But more importantly, because everything that she makes, right, it has to back up with solid science, right? So about the whole provenance and repeatability and reproducibility, right? So the bar is pretty high. So the whole point about digital twin is to try to integrate all these, latest observation. We're talking about satellites, model outputs, and in situ data. And also be able to use this latest observation to drive your next assimilation, your ML predictions. And based on those predictions, you can act on it, right? It could be a mitigation recommendation. This is the kind of thing that you could do. You could maybe tell people to wear a mask with certain sensitivity, or stay indoor, right? These are some of the things that are actionable that, to the general public. But other actionable things could be, retasking an instrument, right? So my project is actually working with the NASA's upcoming mission, Maya, which is looking at PM 2.5 and connecting understanding the impact to health. Is supposed to be launching in 2025. And that instrument actually has a retastable camera. So imagine being able to run your analysis on ground with your model simulation and ML prediction, and use that to drive your next scientific observation, and be able to task all your digital or instruments and focusing on the sensitivity area. Like, for example, if there's a fire smoke start smoldering over in Northern California, right? You want to take a digital observation and not just relying on one single instrument. Let's say you take it, maybe you can ask Topomi to take additional observation as well. So that's the whole part about agility. We call it the new observing strategy. That's the code word for it in the NASA AST program. But think about bringing all this data into one big environment. How do you make sense out of it, right? So you do also need a solution where you can have all this data, model observation, and in situ that's compare them interactively, right? Be able to run these, look at them, and makes it easier for a user, right? You don't want to have the user download a bunch of files and do a bunch of regrading and all that. So our end goal is looking at focusing, delivering near production quality solution. And that means that taking all these interesting technology development here discussed today, how do you make it sustainable, right? We all talk about big data analysis, thinking about a knowledge graph and all of that. These are all interesting work, right? But how do you sustain it? How do you making sure that you can afford it? Do I need to hire an army of people just to keep this thing running, right? So that's the bigger question, right? We all can show some really interesting output, if we have infinite amount of resources. But how, like the end, the NASA, right? And I think, like many of you, working on nonprofit organizations, right? How do you make the solution sustainable? And it means that we have to be smarter about what data to bring in, right? We can just say, well, just bring all the data in one place. This is way too much data, right? NASA itself, we have lots of, we just, the SWAT mission is going to be generate 23 petabyte of data in 3 years. And that's a lot of data, right? That's just one instrument, one satellite. We think about in situ and all that, right? So the new challenge we have to look into is really how do we be smarter about data, what to bring in, and for how long, right? And part of the actionable work for as a digital twin might be relate to the dispatching value-added processing, right? You found something interesting, but you don't have all the information yet. So can I grab some additional measurement, but also put a new algorithm into the system, generate new product, and now we have another observation or another view of the same data. So so being able to be on demand, be able to process value-added data is extremely important. So if you picture that, right, connect all this dot is how connecting the physical world and digital world is it has to be a streamlined process that is in operate 24/7. It doesn't have, and for sure, it's not going to be one computer. It's going to be a collection of systems, and it's going to be leveraging existing solution like the simulation, a model that's the presentation has been discussed today that have experts already been running these things. Be able to pull in analysis by other centers that actually have science experts, right? Data scientists that actually know how to work with the data. So think about is a federated multi-computing architecture that we're building so that now all boils down to be able to be getting all our data, digital assets, right? Data, model, output, prediction, all working together seamlessly, And that's the challenge, and that's the work that some of the folks on the call here working with me, Mohammed in particular, he had to stuck with me every week, right? Sorry. But also Phil, right? So, but it's one thing that we're doing is not just building an island, right? I'm a big open source advocate. I've been building open source software for more than 20 years. And I've been open sourcing software like this, probably 30 JPL package with my name on it, right? Still growing. So the point is, we're building this digital twin as an open source framework. Part of that is we recognizing that we cannot solve the world's problem on our own, right? We need the community to come in, and you bring your data, you bring your model, and you know better how to integrate, how to make it work the right way, right? So we make that as an open source framework, and then we using air quality for wildfire as one of the use case for digital twin. We also building another digital twin using the same framework for hydrology for flood. So a part is to use the best that we have available, right, in NASA to verify and validate our solution, and then make that available and encourage other people to contribute to this work. There's no digital twin standards. I think Ryan can tell you that. I see he's on the call here. But if you have an open source solution that actually brings in different standards and make them work together, right? That speaks volume than a stack of paper with printouts and hyperlinks, because now people can actually touch it and work with it. And so I'm really trying to push this as open source solution for as a reference implementation for digital twins for the community, right? Again, I acknowledge that we cannot build a digital twin just by NASA itself. We just don't have all the data. We don't have all the resources. We build a community. Imagine having a federation of digital twins that you can have them all work together from global to regional scale, right? Everybody else pay for their digital twin, but researcher can just connect these digital twin together and make some sense out of it. And that's my vision. So challenges, there's a lot of it, right? How to get all these things working together. And that's a big part. So standard is a big one. So this is why we are actively working with smart people like yourself. When you talk about what if questions, scenario-based questions, right? People want answer quickly, right? So most large model simulation takes hours, days, weeks, right? How do you get that fast? How do you make quickly, right? You might have to start looking at things like circuit models, right? You might have to have these model continues running 24/7, so incrementally improve these the output instead of having to rerun every single time, right? So looking for an opportunity to do that. Shortage of data. We don't have all the data. As much in these satellite we have, how many in situ sensor, we just don't have all the data. So I'm really excited about the recent Temple instrument, right? So I'm sure you all look at Temple, and I'm waiting for the data, right? They promise should be in sometime in spring or soon. And because that actually will give us an hourly measurement, what's happening in Northern America. That's exciting. Instead of waiting for 24 hours to figure out what's going on, now you get the next measurement in an hour. So we just don't have all the data yet. And now we're fortunate we are in the populated, very industrial modern society here, but there's a lot of area that don't have the sensor data, right? You talk to Mohammed, I asked him, can you get your prediction model to run in this location? He said, we don't have data here, right? So it's a challenge, right? Not every part of the world have the wealth of data that we have. That's a real gap there. But I think at the end is really making things affordable over time, and like basically require people to be here, things outside the box, be smarter about what data to use, what analysis, and when to apply what method. And I think that's extremely important. So I encourage the group to think productions, all right? Think operation. At the end, there's lots of great science research technology being done out there, and JPL been done a lot. And one thing I told the deputy director recently is that JPL did we create a lot of shelfware. They go, what shelfware? But because we created something for 2 years, 3 years, and we couldn't find infusion. It's just stuck in the shelf, and it's very sad, right? So my job is try to get all these exciting technology to in the package, containable, manageable, and affordable solution that we can actually use, for the community. So that's it. I think it's my time up.
Yeah, I think you're doing good on time. Thank you, Dr.
Okay.
Huang. Mavese cannot join us today. Instead, her colleague Sarah Smith is going to share her perspective on integrating air quality data using AI and geographic models.
All right, thank you for that introduction. I'm Sarah Smith, and I'll be hosting this presentation on fusing high spatiotemporal air quality data, some opportunities and challenges. So we've begun with working on a data up and down scaling while we work on co-location. As you can see here in our figure, this is how we were downscaling the ERA5 boundary layer heights through different models. This wasn't particularly my work, but we have been getting a lot done, and this has contributed directly to accessing the data sets that I have been working with. We also have an hourly output of our linear interpolation, including original daily rasters that we have been looking at all over the country where there are EPA and PA data sets. So our goal is to explore alternative methodologies for preparing training data, which could lead to more successful models, such as adjusting the logic for the sampling and averaging meteorological and in-situ data. So our goal is to produce complete training data sets that anyone will be able to use after we've finished. Then we also aim to downscale and upscale in the temporal dimension by considering spotted data input. Delving a bit into the computing investigation with PM 2.5 retrieval, here are some examples of some parameter sweeps that I have been running in WantB, such as XGBoost and PyTorch. So far with the data we've extracted from the prior downscaling slides, we've been working on models in XGBoost to predict purple air and its accuracy to EPA standards. We use variables such as ETA, max depth, and estimators, and a Pearson threshold, which sets a minimum Pearson R between the EPA and PA. So we found that at about a 0.9 Pearson threshold, we achieve a score as high as 0.8719. However, this only uses about 6 out of 64 sensors that we have. So we did another set that was for 0.85. where we have 43 of the 64 sensors, which is a bit more accurate in regards to the data itself. It avoids the overfitting issue, and we reach about a 0.7936 there. We ran something a bit similar in PyTorch with PyTorch's own variables, batch size, learning rate, and epochs, and found that again at the 0.9, we had a pretty high score, about a 0.8645. But on the more accurate one, the 0.85, we found a 0.7677. Moving on, I have a list of the set thresholds and the number of sensors. Of course, we had 64 sensor pairs, so if this starts dipping when you hit about 0.75, we start losing sensor accuracy. So from there, I also include the power usage statistics for the PyTorch and the XGBoost, where we find that XGBoost has a tendency to use more power overall when compared to PyTorch. So there are some sweeps that even use nearly 90% of the GPU percentage, versus the PyTorch regularly uses under 40. So this might be a bit more intuitive to use if you have a lower GPU or not as good as one. So our initial goals here moving forward are to test scikit-learn and TensorFlow models with the same approach to compare the GPU power usage to the results and further examine GPU temperature, memory usage, and so forth. And a final goal we have is to reach a 0.8 or higher R-squared value that is under the 0.9 threshold. So one that is considerably more accurate, such as the 0.85. If we can get a 0.8 R-squared value on that, that would be very beneficial in our research. So delving further into the computing investigation, there was no high resolution air quality data. So what we're currently doing is developing that AI and machine learning models. We're developing those to fill that gap. And right now it takes a very long time to run the model. So this is computationally very challenging, or sometimes even impossible to run on a regular desktop machine. If the training data is well over 5 gigabytes, that isn't sustainable for someone to just run on a desktop computer. So our research and testing approach we've been using is working on these programming models to profile and find hotspots, such as with the earlier raster images, the refactorings, using a variety of libraries and performance tuning, as well as several other approaches. So more initial results and challenges. We've improved by about 50% with XLE compilation for small data. We've reduced our time by 30% by using 64 or 256 threads in the GPU. And we sped up 6 times by using 1 GPU instead of a CPU for 5 gigabytes. So now we just need to work more on rapids and multi-GPU enablement to leverage a bit more for our larger data sets, such as a whole terabyte. Okay, thank you. Our takeaways include formalizing a list of models, linking the pollutant concentrations and various factors like meteorological conditions, emissions, and geographical features, to formalize a list of methods for uncertainty quantification and accuracy assessments, to identify key model parameters and ranges to optimize the model performance and improve accuracy, to collect and share these high-quality training data sets, to develop these data fusion techniques to integrate data from multiple sources into one unified data set, and finally, to work on air quality pattern and event analysis to analyze the changes of spatiotemporal patterns of air pollution due to major air quality events over study regions, such as the Canadian wildfires these past couple of weeks.
Questions? Do we have any questions for the 2 panelists to start with? Okay, here's a question from Dr. Huang. So I think that I'll just follow Manju's practice for you to read a question and offer your response.
All right. So the first question, how do disruptive events such as wildfires and July 4th celebrations impact the prediction model? Can we maintain the same level of accuracy during and after these events? That is a really good question. Lately, we've actually been working on a bit of a book chapter to analyze the wildfires' impacts on air quality and just that sort of thing in general. I know that in my own studies, I've always had to look at the July 4th as the 5 days before and 5 days after are always going to be elevated in July. And that just seems to be a reoccurring pattern that is just established. So that's part of where the temporal part of the analysis kicks in. Because obviously July 4th is going to be different from August 4th, if only for the reason of the fireworks. It's going to be different even if it is around the same meteorological conditions. Does that answer that question?
So the JPL is kind of interesting. We're right next to Rose Bowl. And if you know anything about Rose Bowl, that's where we have the July 4th fireworks every year. So we actually installed a sensor. We bought a sensor on top one of our buildings, collecting measurements like black carbon and all sorts of pollutants right above JPL. And then we have long record of that information. And for that reason, one of the reasons for that, right, you can see before and during and also after. And again, that's for in situ measurement that we're gathering. The prediction wise, right? I think that's mainly the one of my engineers looking at now is, they looking at the direction where these things are heading, right? So one thing that we try to do is just going back to the being agile, instead of trying to bring in all the data, but tracking where the movement of these pollutants, and so that we can actually start pulling the ground sensor measurement for that location into our system and tracking what's going on. So at least we know what people might be subjecting to. We know where this is heading, so we can actually let people know what's going on. So this is more about being a little bit more proactive. So that's an effort that we're looking at. And again, we hope part of the installation of that instrument on top of JPL is actually also helping for collaborations for the Maya mission. So the Maya mission, again, is going to launch in 2025. So we got to use that for cal values. But my instrument on top of that building, just one instrument. So there are other nearby instruments as well. So we also calibrate these measurements by other vendor as well. So it's not, so just in making sure we have the right accuracy. So at least for that, for fireworks, we actually pay a lot of attention just because I'm right there, right next to it. So when breathing it, it's kind of fascinating because every time I show this to my manager, when I put the instrument on top of his office, I just tell him that I care about what he breathes. That's why I put the instrument on top of his office. So, okay, so at least with that, right, that we have some way of tracking, and we also using ML prediction to figure out where this is going.
I was just looking at the question posted by Dr. Huang over especially the second question. It's really the key. We would like to see that, that we don't know if Dr. Tang and Dr. Mohammed has some insights to share about how to integrate the AI machine learning model and geophysical models for air quality prediction. That's really one of the key issues we need to deal with in digital twins.
Yeah. I believe this is a very good question, honestly, and this is what we are working on it right now, because unfortunately, for example, sometimes I see that in computer science community, when they talk about AI and machine learning and data science, sometimes they don't like to use geophysical models, for example, and they want everything to be purely data-driven, extracted from data originally or raw data, especially in deep learning when we use raw data. And on the other hand, there are some people like earth scientists. I see a lot of earth scientists that they don't have a good feeling about AI and machine learning. When we say AI, they really don't like it. The fact is that I personally believe if we can combine these two, I mean, geophysical models with AI, we definitely can get better results. And especially if we can apply geophysical models on raw data to pre-process that a little bit, digest a little bit, and extract some meaningful insights from the data, and then provide that to our AI models, we'll definitely get better results. And I'm sorry. And this is what we are exactly doing right now. We are working on applying some geophysical models on some of our data, for example, meteorological data specifically, and wildfire data, to process some of our sensor data, also to understand and remove outliers or for missing value imputation, this kind of thing, and also interpret meteorological data and wildfire data first using geophysical models, and then apply the outcomes of that and the insights we extract from those models into our machine learning and deep learning models. We will definitely get better results. And it was a great question. We are working on it now.
Yeah, follow Mohammed's comment. So I'm from the physics-based modeling side, so I can say about that. So for the application of atmospheric chemistry models, air quality is only one of them. So to just focusing on air quality, I think physics-based models and statistics-based models, they are all tools. They are not the goals. I want to say, yeah, they both have pros and cons, and I agree. It would be great to integrate both together. It depends on your research, what you are looking at, and your goal of the application. I do see some research happening in this field of integrating statistics-based models and physics-based models. So I saw studies downscaling the physics-based model output using machine learning, and there's studies using building machine learning AI models to mimic the function of the physics-based models. I think those are all valuable research. And I also think we can use AI approach to help improve the processes in the physics-based models. For example, for some parameterizations and building some relations, connections there. So I think it would be great to integrate both, and I see efforts already happening in the field.
Thank you.
Okay. Oh, sorry, Shane. To further off of that comment, as someone from a data science background, it's quite thrilling to see how far AI and those data-driven models can take us in getting a more holistic view overall of not just air quality, but such as what Dr. Wenfu Tang said, the physics-based models. We can go so much further than what we've been doing in the past 5-10 years with the advent and advance in machine learning and AI. So it's very exciting to see how much further we can go from here.
Well, thank you for all the panelists and speakers on discussing those two important questions. Now this floor is still open for the audience to ask questions. You can either type your question in the chat or just unmute yourself and speak.
Yeah, I have a question for the keynote speaker and also the panelists about the uncertainty quantification and the accuracy measurement, either from geophysical modeling perspective or from AI machine learning perspective. How do you quantify the accuracy? And what kind of ground truth would you normally choose to do the quantification of the accuracy?
I can go first. So for physics-based models, normally when you have after you run the model, you get model output. You need to validate or evaluate it with observations, like the surface observations with people are all using, and there's aircraft measurements that's extremely valuable because normally they measure a lot of species and variables. There's satellite retrievals that commonly used. One challenge is a satellite measures the whole column, the whole integrated whole column from the surface to the top, and so when you compare satellite with models, you need to of course you need to match them, but when you compare satellite with the surface quantities, that's something to be careful about. And also satellite retrievals also have some uncertainties depending on the products you are looking at. Sometimes people also use in situ measurements to evaluate and validate satellite products. So in short, you need observations to validate model results. Let's see. So sometimes people do ensemble simulations. That means you instead of running one single simulation, you run an ensemble with multiple members of simulations, and you perturb some initial conditions and to get ensemble results and calculate the average and ensemble spread to understand more of the model performance for that. That's also one way. And also, I want to say for model evaluation, you can only evaluate it with observations. So for the future projection, it's challenging and you evaluate your model for present day and hope it will perform similar for the future projection as it is for the present day. Yeah.
I wanted to add for our predictive models, because they are mostly in our AI predictive models, we predict air quality levels on a ground level. We usually use in situ ground level sensors to evaluate the performance of our model. But we usually use reference-based sensors, specifically EPA maintained sensors that are very high quality reference-based. They are being calibrated on timely basis. So they're the most accurate measurements that we can have from air quality on ground level. So we use them usually to evaluate the results of all models. Although there are many, many different sensors, different types of sensors, low-cost sensors, the sensors that are community maintained, we use them as inputs of our predictive models to get better results. But when we want to evaluate our models, we only use accurate reference-based sensors, usually to evaluate the performance of our predictions.
Do our two panelists have a response to Dr. Yang's question?
That's a hard question, Phil, and you're hiding your face.
Yes, that is hard.
So digital twin, there you go. So digital twin is that kind of interesting, right? Because I remember when I started my talk earlier, it's we creating really one environment where observation models all come together. And the other thing is we have to have long-term records. So definitely it's already creating an environment where we can actually validate the model outputs, because we'll continue bringing in the latest observation measurement from our satellite and in situ. So it's sometimes it might be scary for a model builder, because now they actually have a place that we can see how good their model is or how bad their model is. And so particularly in the flood digital twin that we've been building, we actually support 4 different runoff model together. So that give us a different estimation, right? How much water is getting into the river, and then use that to come up with what's the generalized understanding of where this is. All very much like the weather prediction, right? Most weather predictions like that. You have multiple models. So I think it's if you have the opportunity to try having an ensemble of different model and different condition, and can give you a much better understanding what could happen. But on top of that, you compare with the actual observation. I mean, that's power there. Now, going back to the earlier question about the debate about ML or AI and physical model, well, my understanding is that AI and ML all require long records, right? You need to have lots of data to train your model in order for you to provide better predictions. Just because you have a block of data for the last 5 years, that doesn't really give you a very good prediction there. So in the absence of long-term record, the physical model actually works better because at least you have a way to figure out, well, this is what we know about the physical environment, right? So I think both are very important. If you have a wealth of long-term records available, I would look more into AI capability. But when there's the absence of that, right, then you look into physical model, right? And that's where digital twin, again, so integrated architecture that, be agile, right? Not just one, but, based on this location, we have these kind of data, which model works better, right? So hopefully I answered that question, but the goal is being more agile. The fact is we don't have all the data, we don't have all the model, and some of our model are working better in one region and not so good in another region. And that is another part that we have to think about in terms of building ML in the back. It's not just about prediction, but also how us to be a little bit smarter about selecting the relevant model, relevant data for the kind of research and analysis that we need to do. That's a hard one too. Right? How do you compare? Look at in one region, you have like 6, 7, and 20 different models. Which one should I use? So anyway, hopefully I answered some of your questions.
Challenging? Sounds challenging. So I think we can move on to other questions if the audience have any.
In fact, one continuing question I've always thinking about, but didn't get the right kind of experts in the room to answer. Maybe this is the time. It's a social science question. So that's probably from Fengxiu's perspective, you really want to understand. We know that in order to have multiple domains to work together, especially experts from multiple domains. In this case, we have Dr. Tang from the geophysical side, and Mohammed from the computer science side, and Thomas has a lot of management expertise. So what is the tool or things that you think would best facilitate the collaboration across domains? Or what are the challenges exist that we could be addressed using different either management tools or physical tools or mental tools that we can bring to the picture?
I think this webinar is a great platform to get us together to discuss this. I think more communication would definitely help. I don't know if do people from computer science go to AGU or?
I do.
I go to AGU. I'm a computer scientist, and that's a computer scientist there, Mohammed.
Yeah, I think it'd be good to in those big conferences, we go to other sessions. Sometimes we all go to the same conference, but people go to their sessions that organized by the community. And
very good point, right? I just want to add to that is, for years I've been doing technology development, right? My strategy has been, and this is my secret sauce, so I'm giving out my secret sauce here. When I built my team, I don't just hire computer scientists, and I don't just hire scientists or managers. It's actually my team actually would have technologists and research scientists and stakeholders. One reason for that is when I go give a talk on my technology to a bunch of scientists, they don't want to hear me because they don't want to hear from a computer scientist, right? But if I build a solution and I have the scientists on board and the stakeholder, and they look at the solution and they actually use the tool that I built to address their needs, they can go off and talk to their community with my tool and show it to them. And that speaks volumes because their community will listen to them and not listen to me, right? So I think the way to socializing, right? I mean, you mentioned AGU, but it's great. It's a big conference. Here's the sad part, right? Everybody huddle at the Earth side, the informatics sessions, and all the people in the solid Earth is another side of the building, right? They don't talk to each other, right? Except for beer time. So the part is, if you get the solid Earth guys to work together on your project, right, and you build a solution and have the solid Earth person and give a talk over there, I think that's actually more effective, and it's been very successful for me over the years. So.
Thank you, Dr. Huang. I think Ye Tian has a question.
Thanks for organizing this webinar. So it's quite close to my research interest. So I just hear about your presentation. I just wonder, few of you mentioned about the mobile monitoring of air quality. So I'm a GIS scientist, so I may didn't have so much deep understanding of the atmospheric modeling. So as Mohammed also mentioned, the OpenAQ is a very great open access platform. We can just download the mobile monitoring of air quality data in many cities around the world. However, many researchers also think the mobile monitoring is quite time consuming, and you need to recruit a lot of people. Sometimes you need to have collaboration with the companies. You use their cars to collect the data. So I just wonder, what's your opinion about the mobile monitoring, because it's quite common, and many people believe to some degree it is more accurate than the model for a large scale, like the continental scale. Yeah, that's for my question. Thank you.
I know that the city of Los Angeles has some plan for mobile air quality monitoring. So one of the ideas is to install an air quality sensor on every garbage truck or something like that. And every day when the garbage truck go everywhere over the city, around the city, they measure the air quality, specifically PM 2.5, along with the location of that measurement. And I think that can be a very good data. It can, because as I said, one issue that we have with ground level institute data is that the sensors are very sparse, and the location of at least the high quality sensors are very, very, the spatial resolution is very low. We have only like less than 10 of EPA sensors to measure PM 2.5 in Los Angeles. So that can be a very good model to improve the granularity of in-situ data. I think that's a very good one. And as I said, I know that LA has some plan for that.
Right. Thank you, Dr. Mohammed. Dr. Tao, you want to offer your response?
Yeah, it's more of a question. So what's the difference between this mobile monitor from the EPA station measurements?
So this EPA sensors are like fixed sensors that are installed in a fixed location. And they are very accurate sensors, reference-based sensors that get calibration on timely basis. We use them as ground truth. But mobile sensors can be as sensors that, for example, as I mentioned in this example, we can install them on a bus or on a garbage truck for the city of Los Angeles specifically. So they moved everywhere around the city and measure values. So they are not
Okay.
they are not stationary. They move everywhere.
But they are as accurate.
They are not. I don't think they will be as accurate as those reference sensors. So one issue that we have with those reference sensors is that they are very expensive. They are very expensive. So I think JPL has installed one of them, as Thomas mentioned. So probably you know the price of that, but they are very expensive, and the maintenance of that is very expensive too. But those low-cost sensors, they are like, I don't know, $30, $40, less than $100, something like that.
I see. Yeah, so there's another example, Iagos. I don't know if you have heard about that. So they install instruments on commercial flight and have airborne samples of air quality globally. IAGOS, those are very valuable data. And they also have data for South Africa. I think that's another example for this.
Thank you for the response. I think we have time for one last question before we conclude. Well, if there's no question from the audience, I have a question from a social science perspective. So all the two panel speakers, you all talk about, to some extent, talk about community engagements in your data modeling. I just wondered, to what extent are your models and your data are accessible in terms of skills, expertise for communities that could benefit from your data. For instance, some of you talk about vulnerable communities are more likely to suffer from poor air quality. And Dr. Huang also talked about there's a nonprofit organizations that don't have much capacity for building their own complicated data. So how do you think of those? How do you think of these like environmental groups or social vulnerable communities can actually benefit from your data and modeling in advocacy, or in just to make themselves more informed as a more informed decision maker to engage in government in policy making?
I have to say that these physics-based air quality models are relatively expensive to run. However, we provide a forecast. Take an example of our lab. We provide a forecast for the whole globe and North America. You can access them easily through our website.
Well, the thing is that I think our first of all, right, in our effort is to try to bring all the data that we have available make public, right? So that's one of the effort the open science is trying to do. So that's indeed what I've been trying to do, putting all the relevant data in, making it accessible, right? That's first part. But under the beauty about working, start connecting our digital goods together, that's including model and observation together, including air and ground, right? Is also help us identify gaps, right? So the moment you start seeing the system and say, hey, I see a lot more data point over in the upper North America here, but there's not much data point over in South Africa, right? It speaks for itself, right? Then you know where the investment should go next, right? So one thing that I've been preaching to NASA is that, well, the digital twins actually allow us to bring all the stuff together, but also helping us to find out what are the gaps. Could be data gap, or could be science gap. Like, do we have a model for this stuff? Do we have analysis here? So I think what I've been seeing over the years is that we do a lot of investments, but a stovepipe investment. We have investment on modeling, we have investment in data science, we have modeling in data access and big data and like visualization. They all like, I'm doing great. I can do all this. But the moment you start connecting together, then you start finding that, oh, you're still missing here. We don't have all this. So I think we see an opportunity in the technology when it's available, where we can putting all that good together, make it easier to access. So the disadvantaged community, at least they don't have to go secure HPC environment to run the model. Maybe somebody already have the model in, right? The model output is already there. Right, all they have to do is be able to open a browser somewhere and be able to look at what's going on, right? So the vision is not to try to own all the model, all the data. The vision is try to build a community where they already have sustainable model execution somewhere, right? So right now, I can pull in any kind of sea level rise data, and I don't have to pay a dime for it because the mission's already paying for it. They already have the scientists provision the data. So think about in that model where everyone is providing some kind of digital goods, making available, and you connect them. And I think that will help a long way for the disadvantaged community, that they don't have to procure big machines. They just need to be able to access these services in a low bandwidth environment setting. So
that's excellent. I think that's at least building the first step towards advancing environmental justice, because I think the end goal, right, for all your models and data is to benefit the communities, advance environmental justice. So I think that's we have reached to the end of the time limit. I would like to extend my thank you to all the panelists and speakers for your valuable knowledge and the showcase of your research and the informative discussion. The insights today will pave the way for innovation solutions in air quality management through digital twins, incorporating air quality data and other types of data. I also thank the audience for staying with us towards the end of the seminar. I think that concludes our webinar. We look forward to seeing you in our future events. Thank you.
Thank you.
You.
Thank you.
Thank you all for
Bye,
attending.
everybody.